Hi and welcome to Unit 3 Topic 2, Video for Scalar Product. So this is part of our review videos, reviewing the Unit 1 vectors topic, but adding in that little bit of three-dimensional vector work to help us along the way. And that takes us into Unit 3. So everything you've done with scalar product in Unit 1, which hopefully you remember, pretty much holds true here. So there's a couple of things to review, and they include that it works. This is the three-dimensional vector, x and y. X dot y here, well, it's equal to x1, y1, x2, y2. That's what it used to be. Now we've just got this x3, y3 on the end. That's all that changes when we get to three-dimensional. And if you're still doing that Unit 2 work and heading towards an exam there, you'll need to know the two-dimensional aspects as well. We can also look at the geometric definition, which is that x dot y is equal to the magnitude of x times by the magnitude of y. They're scalars, so it's just multiplying those two numbers together, times by cos theta, where theta is the angle between the two vectors, whatever those two vectors come into that angle of. So the magnitudes, they work out the same. We've still got magnitude calculations based on, so y, for example, the magnitude of y will just be equal to the Pythagorean relationship, y1 squared plus y2 squared plus y3 squared, etc. And so we can do all those calculations the same. It leads to this really nice rearrangement, which you might recall, and that rearrangement is that cos theta is equal to x dot y over the magnitude of x times the magnitude of y. It's a rearrangement of our second equation, and the nice thing is that we can work out the angle between, because we can get x dot y by calculating x1, y1 plus x2, y2 plus x3, y3. So that's not too bad, and you've done that work before. Additionally, and this is a little bit new, we've got these little rules that apply. So the first one is the commutative law. A dot B is equal to B dot A. And we can show that just by considering the fact that A1 B1, well, that's going to be equal to B1 A1. So this comes purely from the fact that commutativity holds for multiplication, and so therefore it will hold also for scalar products. And A dot B plus C is equal to A dot B plus A dot C. Sorry, there's a squeaking in the background, I'm not sure what it is. And you could go ahead and prove that again, just with A1, A2, A3, B1, B2, B3, etc., and just show that works. It's pretty easy. We also have this rule with relation to K, which is a scalar, so a number, 7 or -2 or something, can be distributed into the dot product. And we also have this, and this one's pretty important. A dot A is equal to the magnitude of A squared. And if we consider this, A, and there should be little squiggly lines on there, A dot A is equal to the magnitude of A times the magnitude of A times cos. Now A and A are in the same direction, so it's cos of theta. And cos of theta, of course, is 1. So, sorry, cos of theta, cos of 0, and cos of 0 is 1. So therefore we'll get the magnitude of A squared. So that's handy as well. That'll come in and it's useful for you to remember. If A is perpendicular to B, then A dot B equals 0, because cos of 90 is 0. If A is parallel to B, then A dot B equals the magnitude of A times the magnitude of B, because cos of 0 equals 1, as we've just seen here. And of course we've got our components as well. I dot I equals 1, J dot J equals 1, K dot K equals 1, and I dot J equals 0, J dot K equals 0, and I dot K equals 0. Because the first row are all parallel, and the second row are all perpendicular. So that's where we get that relationship from. And that's a summary about all you need to know about the scalar dot product. Except to recall, of course, it is called the scalar product because you get a scalar answer. So don't forget that, you're looking at a scalar answer. Otherwise, you should be fully able to do exercise 4D now. All the best.